All right, let's just jump right in. Think about it for a second. From the ice clinking in your glass to the steam rising from your coffee, we're literally swimming in different states of matter every single day. But what's really wild is that the simple rules that govern all this stuff, well, they can take us from our own kitchen to the most bizarre and extreme places in the entire cosmos.
Have you ever really looked at a single drop of water? How it beads up, trying to pull itself into a tiny little sphere? It seems so simple, but it's actually a massive clue. It tells us that all matter, everything, is made of tiny particles that are always moving and always pulling on each other. And getting a handle on that constant push and pull, that's the key to, well, pretty much everything we're going to talk about.
So let's start with the basics you probably remember from science class. But we're going to look at them from the inside out, right down at the molecular level. It's like this hidden dance that's happening all the time, and the amount of energy the particles have, that determines all the moves.
Okay, first up, solids. I want you to imagine a perfectly organized, super tightly packed crowd at a sold-out show. Everybody's got energy, they're all kind of vibrating in place, but they can't switch spots or wander off. The forces holding them together are just too strong, locking them into this rigid structure. That's exactly why a solid, like an ice cube, holds its own shape.
Now, let's turn up the energy a bit. In a liquid, those particles are more like dancers on a really crowded floor. They're still packed in close, constantly bumping shoulders, but now they've got enough juice to slide and weave past one another. That freedom to move is precisely why a liquid can flow and take the shape of any container you pour it into.
And if we crank the energy way, way up, we get a gas. Now our particles are like a handful of people just zipping around a massive empty warehouse. They're moving so incredibly fast and are so far apart that the forces between them are almost zero. They just fly around, bouncing off the walls, which is why a gas will always expand to fill whatever space you give it.
So if solids, liquids, and gases are all about how much energy their particles have, how do we actually change that energy? How do we get from one state to another? The answer, as you probably guessed, is simple. You turn up the heat.
But what's really fascinating is how that heat actually moves from one thing to another. Just look at this diagram. When you stick a cool spoon in hot water, the super fast water molecules are literally crashing into the slower vibrating atoms of the spoon. And in every single one of those tiny collisions, a little bit of energy gets transferred. The water molecules slow down, and the spoon's atoms speed up. And just like that, the spoon gets hot.
And this whole process has a name: conduction. It's simply the transfer of energy through direct contact, particle bumping into particle. It's so important to remember that heat isn't some invisible substance. It is the movement of energy from something with more of it to something with less.
So this lets us map out a kind of energy ladder that works for most stuff we know. You start with a solid, you add enough energy to hit its melting point, and bam, its particles break free and it becomes a liquid. You keep adding energy till you hit the boiling point and poof, those particles escape entirely and become a gas. Simple enough, right? Well, you know the universe is rarely that simple. It turns out the lines between solid, liquid, and gas can get wonderfully blurry when you get the conditions just right. And that's where we find some truly strange phenomena. I mean, what if you could just jump straight from a solid to a gas, completely bypass that whole liquid phase? It sounds like something out of science fiction, but I bet you've actually seen it happen. The phenomenon is called sublimation, and the classic example is dry ice. You see, at the normal air pressure we live in, solid carbon dioxide doesn't melt. It just turns directly into that spooky rolling fog of CO2 gas. That's why they call it dry ice. There's no messy liquid phase to deal with.
And this is where things get really cool, because it shows us that temperature is only half the story. Pressure is a huge deal. A phase diagram like the one you see here is basically a map for matter. And if you look at the map for carbon dioxide, you can see that for it to ever become a liquid, you need to be at a pressure that's more than 5 times higher than our normal atmosphere. Since we live way down in that low pressure zone at the bottom of the graph, it just always sublimates. Okay, now on that map, follow the lines that separate solid, liquid, and gas. See that one single, unique spot where all three of them meet? That is called the triple point. And it is this mind-bending, precise condition where a substance can be a solid, a liquid, and a gas, all at the exact same time, all in perfect balance.
For water, this magical point happens at just a tiny fraction of a degree above freezing, but at a crazy low pressure, about 165 times lower than the air pressure you're feeling right now. If you could create those exact conditions, You could literally watch an ice cube that is simultaneously melting into a puddle and boiling away into vapor. Just incredible. So we've got solids, liquids, and gases. But here's the kicker. It turns out these three states that we see all day, every day, they're actually incredibly rare in the grand scheme of things. The vast, vast majority of the universe exists in a fourth, much more energetic state.
99%. Just let that sink in for a moment. 99. What on earth could possibly make up 99% of all the regular matter that we can see out there?
That number? That represents plasma. Everything we've talked about so far, the solids, liquids, and gases that make up Earth and the other planets, that's just the leftover 1%. The stars, our sun, the vast emptiness between the galaxies, that is all plasma. So what even is it? Think back to our energy ladder. If you just keep heating a gas to insanely high temperatures, the energy becomes so intense that it literally rips the electrons right off of the atoms. What you're left with is this super hot, glowing soup of positively charged ions and free-floating electrons. It's kind of like a gas, but now it's electrically charged. And while plasma is truly the stuff of stars, we've actually managed to harness a little bit of that starlight and put it to work in some surprisingly common technologies right here on the ground.
That's right, from the glow of a neon sign to an old plasma TV, we've been using it for a while. But today, its real power is in high-tech manufacturing. See, because plasma is made of charged particles, you can control it and guide it with incredible precision using electric and magnetic fields. That amazing property is what lets us etch circuits onto microchips that are impossibly small, or sterilize delicate medical tools without ever touching them.
Solid, liquid, gas, plasma. Okay, that's got to be it, right? That covers just about everything? Well, not quite. When we push matter to the absolute, bleeding-edge extremes of temperature and energy, things get even weirder. At the coldest temperatures we can possibly create, just a fraction of a whisper above absolute zero, atoms can slow down so much they actually lose their individual identities and merge into what's called a Bose-Einstein condensate, where thousands of atoms act like one single quantum object. And at the other extreme, inside particle accelerators hotter than the core of the sun, we've actually created quark-gluon plasma, where the very protons and neutrons that build our atoms melt down into a soup of their most fundamental parts. We've gone from a simple drop of water all the way to states of matter that challenge our basic ideas of reality. We know about things like supersolids, which are somehow rigid like a solid, but can flow without any friction like a liquid. So it really makes you wonder, right? What other bizarre, unbelievable states of matter are still out there, existing at the very edge of what we know, just waiting for us to find them?